So at its most basic, right? Metabolism is about generating energy. It's about making ATP. And to make that ATP by breaking down, the slide calls it foodstuffs. I tend to call it a substrate. Substrates can be carbohydrates, fat, protein, okay, something that has carbons in it, generally, right? We have to have metabolism. We have to have a way to make, it's not what makes the wrong word, we have to have a way to recycle and regenerate ATP within your muscles, or you can't continue to exercise. That's the really important thing, right? All movement and most of our body functions require energy, they require ATP, and we have, as you will see in a couple of slides, a very, very small amount of stored ATP in any given tissue. So we have to have these pathways to break things down and recreate that ATP, or you're gonna die. Right? That's the end of the kind of end all be all. Brain needs ATP or it dies. Your heart needs ATP, it can't beat. Diaphragm needs ATP so it can contract, and we can breathe, et cetera, et cetera, et cetera. Okay? I'm much less morbid, which I'm sure is great with my voice like this. Right? The significance of metabolism is that many of our physiological responses that we're going to talk about next in class occur in direct sort of response to changes in metabolism, and they change to support our ability to make more ATP. Changes in breathing and respiration, changes in heart rate, cardiac output, and changes in the hormones that are released during a bout of exercise. Almost all of those things are going to occur because we need those changes to support. Okay. If I ask any of you to stand up and do some squats, or about 50-50 on the class assessments. Some of you are like, the squats are great. We like to get up and move. Some of you are like, fuck those squats, right? No more. I understand. If we had you stand up and do something, you start generating force, breathing goes up immediately, heart rate goes up immediately. You begin releasing hormones like epinephrine and norepinephrine. They're going to play roles in vascular changes and in metabolizing fat, breaking down glycogen to be able to help metabolism, all of which we will get into. Okay. Additionally, many training adaptations, especially aerobic training adaptations, are going to be proportional to the metabolic stress that we put the body under during a bout of exercise. Okay. If you're an athlete, and by athlete, I mean Ellis and her little cross country team. We had a boy, I tell you on Monday that we had our first cross country. And she ran, we had a boy who just up on like the day before that ran in her race on our team and he won. Admittedly, he was one of the oldest ones, but just shows up, does good. Ellis was lollygagging around. She ran the whole race, I was very proud of her. But our performance in very long distance events and in sprints, okay, maybe not like 50 meters or 100 meters, but 200 meters, getting out to about 400 meters, like half a lap on the track, maybe up to 1 lap on the track. Performance is very, very often limited by the rate at which we can make energy available, at which we can make ATP available. Okay. And we'll talk more about the specifics of all of that. So there's this kind of weird zone in the middle and stuff that's controlled by lactate and some stuff. And then there's sprinting stuff that's controlled by the creatine phosphate pathway, which we'll get into. Then there's the very, very long distance stuff like marathons, half marathons, That's controlled in large part by our ability to have mitochondria and aerobic metabolism. So we'll tease out some of those things, okay? Now, the last bit, we talk about fatigue, and we will say that fatigue can be caused by a decreased availability of energy or an accumulation of metabolic byproducts. So when you go exercise, okay, when you tax your metabolic systems, you're going to have a lot of ATP turnover, and some of that will, at some points, inhibit your ability to generate force. Okay, it will also make you feel, perceive that the exercise is difficult. Okay, whenever you stand up, you do something, your legs are burning. That burning sensation is caused by metabolic byproducts. It's caused by hydrogen accumulation from the formation of lactic acid. So we need metabolism to get us the energy to exercise. We also need metabolism, right? Sometimes by running metabolism too much or at a very, very high rate, there are these byproducts and things where maybe you can make the energy, but you can only make it for so long, and then you're gonna have to stop. That's gonna lead to fatigue. So lots of stuff is gonna interact with metabolism, okay? All right, so let's start by talking about energy. We'll talk very, very, very briefly about thermodynamics because I think it's important for how we understand everything. Energy is defined as the ability to perform work, right? So we need energy, we need ATP to get muscles to contract, to perform work, right? Force multiplied by distance. If you think about energy from a chemistry standpoint or physics standpoint, energy is one of these kind of weird things that emerges when a change takes place. You know, like what is that change? What do you mean? This is a very kind of esoteric way of thinking about these things. But if you think about it as sort of bioenergetics and thermodynamics, it's the flow and exchange of energy within a living system. Okay? You have energy in your body. You use that energy to contract a muscle, to repolarize a neuron, okay, to digest food, to think, right? You're using that energy. You've then eaten something, and then you break those foodstuffs down, and it recreates that energy. So, in essence, then we're flowing energy from, right, something we ate into our body, and then into whatever we need our body to do, to move, to think, digest, something like that. Okay. And that gets us into this idea of thermodynamics. So the first law of thermodynamics says that energy cannot be created or destroyed. Okay. It is transformed from one form to another, not being depleted. And so if we think about what's happening in your body during exercise or any other time in relation to this, what that tells us is just you have some ATP, you strip the phosphates off to allow you to do things. Okay. We're using that energy, and then we're going to bring foodstuffs in and break it down. And in that breakdown process, we're gonna put a phosphate back on and remake the ATP. We're going to break it down again, and then we're going to resynthesize it. We're going to break it down again. We're going to resynthesize it. Okay? And so that explains this idea or this flow of energy we're going to have. It also, in some ways, explains some of the ideas behind when we eat too much. Okay, we bring in excess calories. We don't need all of that for our daily activities. So we store it, right? We will take those, and rather than creating ATP, we'll store it away in glycogen, or we'll store it away as fat in adipose tissues. Okay. Similarly, you will see that in that same idea that if you eat less than what you need, you will start breaking down those stores of adipose tissue, those stores of glycogen, because we're just shuttling around where the ATP is, where it's coming from one place to another. Okay? This idea makes sense. Because I think it's really, really important that we appreciate that you have a very small amount of ATP in any cell in your body, a really small amount. And because of that, you have to have these metabolic pathways that can turn on immediately to resynthesize that ATP. Okay? Like one contraction's worth of ATP, two contractions worth of ATP stored in a muscle. Very, very low amounts. Okay? And that's why we have to understand how these pathways work. Because how fast they can synthesize things, how many steps they have, the substrate they break down, all plays a role in can you break down enough to get enough ATP back to that muscle to allow it to continue to exercise. Okay. Questions so far? Okay. All right, I'm talking about ATP. Maybe I should have led with ATP, but we have general information about ATP. Okay. We measure the ability to make ATP on something in calories. Okay. That's essentially what you look on the back of whatever drink you have, if you're eating breakfast, which I can see some of you are. Shame on you, we're not supposed to have food in here. I say, as I bring food almost every day. Okay, right? When it says calories on there, that is basically telling you how much ATP you can synthesize or you can resynthesize from the foodstuffs in whatever you can. Okay? The use of ATP during exercise is going to denote the intensity of that exercise. And I think intuitively that should make sense. Okay. If I'm standing here, I have a lot of muscle contractions, so I don't need that much ATP. Right? If I start shuffling sideways, I'm moving, and I'm using more ATP than I was when I was standing. The intensity has gone up. I go from shuffling to shuffling fast. Okay. Then ATP, I'm more muscle contractions, more cross bridge cycles, then ATP use goes up even more. Okay. If I went from shuffling to running, right, even more, to sprinting, even more. Okay. That's the idea of how we determine exercise intensity. The rate of ATP use per muscle contraction varies among the fiber types. Okay. Slow twitch fibers, their myosin ATPase is more fuel efficient, basically, than type 2A and type 2X. So when we hydrolyze the ATP, when we break the cross bridge using the myosin ATPase in the slow twitch fiber, that costs us less energy than if we're doing it in a type 2X fiber. Okay. So those of you that have more type 1 fibers are more ATP efficient any given force production level or any given ATP use level than people that have more type 2s. And that can become really, really important from a metabolic standpoint because if you are more efficient, it's kind of like having a car that gets better gas mileage. Right? If you have a finite amount of ATP, it will use it up slower if you have more type 1 fibers, or you'll be better able to match and resynthesis, the rate of resynthesis to what's being used if you have more type 1 fibers. Okay. Okay. I will, for the 14th time, tell you guys that energy stored as ATP in a cell is extremely low. Extremely low. Okay. To have enough to do multiple kind of longer duration sustained contractions, your entire cell would just have to be ATP. It's all that would be in there. There'd be no room for anything else. Okay. And so the way that animals and in some ways like single cell organisms like bacteria, the way that things have evolved is rather than having a large storage capacity for ATP, we have these metabolic pathways that will allow us, as the ATP is broken down, to reform it again. Okay. And so that way we will store extra foodstuffs and things at various places in our body, and get them in our bloodstream after we've eaten, and we'll run the process that way rather than you just have this giant store of ATP. Okay? How do we get more ATP during exercise or at any point? There are several pathways, okay, and there are several substrates. So by substrates, I mean the thing that gets broken down. Each individual metabolic pathway will use one or a couple of different substrates. Each individual metabolic pathway has, depending upon what it breaks down, has a different number of steps, and also then yields based upon what it breaks down a different amount of ATP. So because of that, you'll have some pathways that are faster than others. We tend to use those first. You go from rest into exercise. Then you'll have some pathways that are slower, but very often the slow ones allow us to make most energy. And so there's this kind of push and pull and balance on all of those that we have to find. Okay, I'm going to say something now that will be reiterated later on, but is the first point, I think, where depending upon who you've had in previous classes and things, this may be the first time you encounter this or that we'll talk this. Every metabolic pathway is active all the time. Every metabolic substrate in almost every instance is being used all the time. Okay? All the pathways all the time. One caveat to that is maybe if you're doing a sprint, you deplete all your creatine phosphate, but creatine phosphate is being used while they're sitting there, even though you're not doing kind of high intensity stuff. So you look a little sleepy when you get up and do some squats. But you're using creatine phosphate, you're using fast energy just sitting there. You're using glycolysis, you're using oxidative phosphorylation all the time. Okay? And that's the part that's conceptually difficult, is because they're all active, but based upon the ATP demand, different pathways will different pathways will provide more or less energy as a percentage of the total needed at different times and in different circumstances. Right? The pathway and substrate that will be used, or the one that will predominate, is going to depend upon the mode of exercise. Okay? Are you running? Are you biking? Are you rowing? Are you doing resistance training? Especially depends on the intensity of exercise. Is it low intensity? Is it moderate? Is it high? Okay. The presence or lack of oxygen is pretty rare. We don't have oxygen. In some instances, when you do high intensity resistance training, like during the contraction or muscle generating force, you may have a little bit of a lack of oxygen, but then when you rest, because you rest, the oxygen comes back. That's not a really big deal. The most common time when it's not really a lack of oxygen, there's less oxygen, is you go to altitude. Okay. Anybody's ever been to Colorado, if you've been to Denver, Colorado Springs, or you've gone to Rocky Mountain National Park or someplace, just one of my wife and I's favorite places. Anybody been to Rocky Mountain National Park? Like 2 people. Okay. There was snow at the Alpine Visitor Center last week, which is like one of the highest national park places in the country. You know, it's September and they had like a foot of snow. It was great. But as you go up, there's less air, so there's less oxygen. And that can have dramatic effects on exercise. When you try to exercise or run at high altitudes, it feels worse because it's worse, because there's just less air. Your state of training, those of you that are more or less trained as an endurance athlete, especially will have different amounts of mitochondria, okay? And that affects which pathways we use, which substrates we use, and then your diet. Anybody heard of, oh gosh, why can I not think of it? It's the one where you don't eat carbs. It's happening this morning. The keto diet. Has heard of the keto diet? Okay. Basically, you eat no carbohydrates. Okay. You eat a bunch of protein. Seems great. You just eat bacon all the time, right? Protein and fat and these kinds of things. When you do that, there's no carbs. You break down your glycogen. Then we have to change based where we're getting our energy from. So you eat more fat, you metabolize more fat. You eat more protein. In a lot of instances, that protein goes to the liver, it gets converted into amino acids, and then the amino acids get made back into glucose through a process we'll see in a minute called gluconeogenesis. But you have very low carbs. And so preferentially, that if you go to exercise, you will use less carbohydrates just because you've been eating less. Okay? If you just go and smash a bunch of pasta, I recommend this to everyone. I love carbs. Don't know why. Carbs and salt. That's the thing that gets me. Right? Garlic bread is my favorite thing in the world. Some breadsticks from the Olive Garden. Oh my gosh. Okay. To eat a bunch of carbs, guess what you metabolize more? Carbs. Okay. More carbs. That's just kind of the way that it goes. And we can get into more later on about are carbs good, are carbs bad, are some carbs better than other carbs, are there good carbs, are there bad carbs, what happens with the keto diet, blah blah, and all of those things. There's a lot of nuance that goes into that, but in general, what you eat can also influence what you're going to metabolize. And because of that, what you eat before a exercise competition can actually influence your performance in some instances. And we'll use some examples of that there. Okay. So here are three primary energy substrates: carbs, fat, protein. We're gonna talk about carbs, and I'm gonna use glucose as the example molecule most of the time, because if you have a different carbohydrate that you've eaten, you had some high fructose corn syrup or something, right, which is the enemy of everything. If you had some fructose, if you had some maltodextrin, if you had sucrose or something, in a lot of instances, when those things get metabolized, they just get converted to glucose and then broken down from there. There's just an extra enzymatic process. So we'll use glucose as our sort of sample or representative carb. So when I say where carbs get broken down, I'm always going to say glucose, but the other carbs, other sugars are going to get put in the same place. That's the molecule. Our storage ability for glucose is something called glycogen. Glycogen is just a bunch of glucose molecules hooked together. Okay? You have glycogen in two places in your body. You have glycogen in your muscles and you have glycogen in your liver. And the stores that are in those places, they're not super big, and we're going to use each one at different times. Okay? At different times. Who hasn't had breakfast? This every day. My non-breakfast people, you're probably dumping some carbs out of your liver into your bloodstream to keep your blood glucose elevated right now or at a regular level. Okay? You tend to use liver glycogen to provide carbohydrate to maintain blood glucose levels. That can be important during exercise, but that's its primary role. Muscle glycogen is there for providing carbohydrates right into glycolysis in the muscle. Okay? They're not really controlled by blood glucose. You primarily use muscle glycogen when you're doing muscle contractions. Okay? We'll get into a couple of the signals, some of the hormonal signals and things a little bit later on in class to control each of those. When I say fat, I mean lipids. Okay? You are generally have some lipid tissue floating around in your blood, bound up as chylomicrons, bound up on albumin, some other kinds of proteins, right? Fat doesn't mix well with water, which is what blood mostly is. So anybody that went and had a Chick-fil-A chicken biscuit this morning, you guys have some adipose tissue, you have some lipid tissue in your blood right now. Also, the next time you go, let's bring one for everybody. Typically stuff is going to be in your blood as free fatty acids, that's what we're going to say. It's sometimes in your blood as cholesterol molecules. we tend to store extra fat in the body, okay, in what we call adipose tissue. You have adipose tissue under your skin, subcutaneous adipose tissue, flabby tricep, okay? You have adipose tissue or lipid that's stored in your muscle. You have some stored around in between the individual muscles. You also have some actually down inside the fiber itself, which is really kind of a fascinating thing. And then we have fat on the liver. And where the fat is, liver fat, sort of your belly fat, those kinds of things can be predisposed to cardiovascular disease and diabetes and things. And so the storage side and stuff of this can have some problems. But from a metabolic standpoint, the point of storing fat is that we have a vast energy sort of backup. Okay, vast energy backup, as you guys will see in a couple of slides. You have days, weeks of energy stored as fat in your body. That way, if you don't get any food, you don't get to eat, you have multiple days or weeks of stored energy to be able to sustain life after all of that. Okay. You guys have all had health and fitness, you know, ladies in general, you guys typically have a little bit more stored fat than the guys. That's about childbirth. Okay, it's about being able to carry a child to term if you're essentially needing energy for two or three or four or any, if you're having moments. That's one of those things for that. Okay. Protein, we're not going to talk about protein very much. Protein, you eat the protein, you have protein stored in your muscles and in some other places. To metabolize the protein, you have to break it down into its constituent amino acids, okay, through catabolism. And we then convert those amino acids to glucose through a process in the liver called gluconeogenesis. In some instances, you can stick the amino acids directly into the Krebs cycle. Much more often, it's going to be gluconeogenesis. We typically only use protein as an energy source when we're in a caloric deficit, right? We're in a place where we're not getting enough carbohydrate and fat from our food to be able to do things, okay? So this is one of the things where if you want to build muscle, you gotta eat, right? You gotta eat, because if you're in a negative caloric balance, then there's going to be some ability or some want to kind of catabolize protein out of the muscles you're trying to build potentially and use it for energy because you're not eating enough. But we'll return to protein a little bit later on, but it's much less prevalent as an energy source, at least for our purposes in class. Okay, fun with words.
Can I make a, oh wait,
No, please go ahead, Ty.
probably what you're about to touch on. Please, for the sake of like grading and things, know the distinction between these. They're all very similar words, but if you put like gluconeogenesis when you mean glycogenolysis on the exam, like they're all very similar words. This isn't grammar, but like just know the difference and know how to spell them differently, please. I want to be able to give you points where you've earned them.
Okay. Don't upset Ty. Don't make Ty sad when he grades your tests. Those kinds of things. We do get sad when we grade. We also get happy, but you know, it's like, oh, we missed that. Okay, that makes us sad. Fun with words. These are a bunch of words that relate to metabolism. They primarily relate to carbohydrate metabolism, but they all look and sound relatively similar. And so I want to talk you through them and make sure that you can understand that distinction so you don't make Kai sad when he grades. So there's a process called glycolysis, okay? Glycolysis. Glyco meaning carbs, lysis meaning break down. Glycolysis is a metabolic pathway where we break glucose down into, it goes all the way through into lactic acid and ATP. That's glycolysis, okay? There's a process called glycogenesis, which is not making glucose from lactic acid. It's not the reverse of glycolysis. Glycogenesis is making glycogen from glucose. You eat a bunch of pasta, or you eat a bunch of Starbursts, which are my favorite. Hint, hint. Then you have excess carbohydrates. You will try to make some of those excess carbohydrates into glycogen. That's glycogenesis, carbohydrate generation. Okay. Then there's glycogenolysis, that's the reverse of glycogenesis. That is taking glycogen and breaking it back down into glucose molecules. Okay, that's glycogenolysis. This is primarily controlled by an enzyme. And I do want you to know this enzyme. The enzyme that leads to glycogen breakdown is called phosphorylase. As you can see, eyes pointing to where it is on the handy dandy worksheet. Okay. The reason you need to know phosphorylase is there are hormones and other signals that increase at various exercise intensities that activate the phosphorylase, make it break glycogen down to a greater extent. This is one of the places where we can control carbohydrate metabolism. The last word we've mentioned a couple of times is called gluconeogenesis. It's making glucose in the liver from a non-glucose substrate, mostly amino acids from proteins. Okay? Mostly amino acids from proteins. So those are 4 words. They all sound relatively similar. I'm sure you can all now envision a lovely all of the following except a multiple choice question that has all of those words and being very tricky and sort of slightly twisting around what one of them does or means. Okay. So please learn those and keep those straight. We will talk till our eyes are bleeding about glycolysis. We'll talk a little bit about gluconeogenesis, and we'll talk about these 2 processes, most of the breakdown of glycogen, just as kind of a broader process. Okay. I got real serious when you put up the worksheet. Ooh, worksheet. Let's do it. Okay. How much of these energy substrates do you have stored in your body right now? If you remember a couple of slides ago, I said you don't have that much carb. You don't have that much storage energy. It's carbs. You see if I can make, of course, the Zoom thing go away so that you guys can see. Okay. And an average, you can say 140-pound person with 12% body fat, which is average of no one. A lot of these things were like done in the 70s when we were a smaller group of those things. But you've got, most of you probably have somewhere between maybe 1,200 and 1,800 kcals or calories of stored carbohydrate in your body. Okay. You've got most of that, or the majority of that is going to be muscle glycogen, and then you've got some liver glycogen. Okay. Conversely, this is a very lean person with 12% body fat. That person has about 72,000 calories stored in out of those tissue. Okay. 72,000. And you imagine, right, if y'all got really, really desperate, you were resting metabolic rates, which are lower than most people think they are, right? That 140-pound person, they just sat around and watched Netflix all day, might need 1,000 calories, 1,100 calories or something. So they've got, right, months basically of stored, so enough stored fat. You have these very, very, very large stores of energy as fat. And this is why, right, you don't need to eat enough, or you go on Survivor, right? You watch Survivor, the 1,000 seasons, you go on Survivor and everybody loses fat because they're having to break that tissue down when it's not getting to eat. Okay? Please, I want to be very clear, I'm not advocating, 1, for going on Survivor, 2, for depriving yourself of food. Okay? We all need to love ourselves and our own kind of ways. Okay. Please eat a normal amount and make yourself happy. Thanks for coming to my TED Talk. Okay. Let me see how much time I got. Okay, good. We can kind of get through the first, please. Now, I'm gonna get you guys, we're gonna talk our way through the metabolic pathways. Okay? We're gonna take them one after the other. We're gonna talk about them independently, so I can show you what goes in, what comes out, how much ATP you get, what the enzyme is that controls it. Then, once we've done that, at the end, we'll come back and try to do what's on the worksheet and show you how they're all kind of working together and how when one goes up, how that affects the other. So we're gonna start this kind of what I imagine is like how you guys have seen them before. Okay, so we're gonna break these down into kind of three primary categories. We have a couple of pathways or a couple of substrates that will get us energy very, very fast. Tend to call those the immediate pathways or the phosphagen pathways. They're short, they're simple, okay? That's what makes them fast. We'll get into those. Then we have what's kind of loosely called non-oxidative, and that's glycolysis. Right? It's non-oxidative because
It doesn't use oxygen.
it does not use oxygen. Very good. Right? That's a very, very key thing. Glycolysis does not use oxygen. I promise you that will be on the test. And then we have the oxidative, or we typically call the aerobic pathways, which are many of the things that are downstream of glycolysis, recycle, the electron transport chain, which oftentimes are collectively called oxidative phosphorylation, or the aerobic metabolic pathways. Those are all kind of used interchangeably. Okay, we're going to start with the immediate ones. Okay, with the immediate ones. Okay. So if you look at this, what this figure is trying to demonstrate is time of exercise on the x-axis and the relative percentage of all of the ATP used during exercise, the pathway from which it originates. Okay, and I apologize, like the x-axis is not really to scale. At 10 seconds, 30 seconds, a minute, right? And we're spreading out these kinds of things like this. What you can see is that in solid line, in very, very short duration exercise, things like 10 seconds or less, a lot of the energy, a majority of the energy comes from these immediate phosphagen pathways. But the other big takeaway is then as the time increases, we in essence use up after about 30 seconds, we use up all of the phosphagen pathway energy. And then you'll see here in the small dashed line that glycolysis ramps up and is going to provide the majority of the energy. And then over time, it's going to fall out, and there's going to be this kind of gradual increase over a couple of minutes and then a leveling out of the oxidative pathways. Okay? So that's kind of how all this is going to fit together, but we're going to talk about the immediate ones first. So the things that are going to, I say, stand up, do some squats. What's going to give you the energy to do those squats right now? Okay. So we talked about that there's stored ATP. Now the phosphagen pathways, the most prominent one that has the largest capacity to get us energy, is a pathway that we call the creatine phosphate pathway. Okay, creatine phosphate is a molecule of creatine with a phosphate hooked on the end. It's just what it says that it is. Okay, you guys eat creatine in your diet, it gets into your muscles, and then you take an ATP molecule, pull a phosphate off, stick it onto the creatine phosphate, and then it just sits there and it waits. Okay? We get the creatine from your diet from meat and fish or from taking some type of creatine supplement. Eat a couple of cans of tuna fish a day, you'll get just as much creatine as if you go to GNC and buy some. Okay? It's a naturally occurring thing. About 98% of all the creatine and therefore the creatine phosphate is in skeletal muscle. Okay. And when you eat extra or consume extra creatine, this is really important. For about 80% of the population, you can increase, if you're what we call a responder, you can increase your muscle creatine phosphate levels by up to about 20%. Okay, up to about 20%. So if this is an immediate energy pathway, you eat extra creatine, you then have more creatine phosphate in your muscles, you have more immediate energy to use in a bout of exercise. That's one of the ways that we think creatine phosphate helps augment resistance training, is it's not anabolic in and of itself. It doesn't drive protein synthesis by itself, but maybe it gives you a little bit more energy and it lets you do one more rep or something like that. And that one more rep drives a larger mTOR activation, a larger anabolic process. Okay. When you need to break down creatine phosphate to recapture the energy that is stored there, the reaction looks like this. Okay. I'm sorry, I know we say chemistry, some of you want to hide under your desk. I totally get it. Okay. This is what's called a redox reaction. It's reversible. It goes in both directions. You don't have to know that. It's gonna be okay. But when we expose, right, we expose creatine phosphate to elevated levels of ADP inside a muscle cell, such as when we're beginning to exercise, we're running a cross-training cycle, we're running circa, we're running the sodium potassium pumps, we're breaking down a lot of ATP that we have stored. When that happens, ADP levels go up. From chemistry, if something on one side of the equation goes up, it drives us in the other direction. So when ADP goes up, it drives this reaction in this direction. And so we're going to take the phosphate off of creatine phosphate, stick it onto ADP, and make ATP and creatine. Right? One step. That's why it's so fast. It only requires one step. I start doing curls, ADP goes up immediately in my muscle, immediately start grabbing phosphates off of creatine phosphate, hooking it back on so I can make more ATP, or I can really make that ATP. Okay. Outside of simply using the stored ATP in your muscle, this is the fastest metabolic pathway. It gets us energy the fastest. Because of that, it tends to be the one that we use first. The one we use when we go from low ATP demand, low energy use, to higher, because it gets it to us right. Right? And it's fast because it's one step. One step. That's what makes it fast. Our problem with this is that the total amount of energy we have stored as creatine phosphate is actually very low. Right? Your muscles have creatine phosphate, but they're not all creatine phosphate, just like they're not all full of ATP. And so there's a finite amount. And most of us, there's enough creatine phosphate that lasts us maybe 10 to 20 seconds. Right? Just about long enough for those of us that are a little slower to run 100 meters. Those of you people that are like world record, like really, really fast, begins to run about 200. Or you can think I can do 4 or 5 reps resistance training. Okay, we will come from here on Friday. Thanks.
Yeah, just hang on to these. They're study guide material. You won't be turning these in, okay? And for those of you on Zoom, there's a digital copy.